So this is our first lecture in probably the longest chapter in the textbook. It's chapter 9. I devote more lectures to it. It covers a range of topics. The authors of the textbook could have basically had a whole chapter just on internal combustion engines, then a whole chapter just on gas turbines, both for power plant, like electricity production, as well as for propulsion systems, like on an aircraft jet engine, as well as a whole chapter in just compressible flow topics. They could have. But anyway, it's all packaged in one chapter, so there's a lot to cover. Today we're just going to cover the basics of internal combustion engines and then the Otto cycle. Yes, some of you had this in Thermo 1. True? Some of you didn't. But hey, it's fine to have a little review every now and then. We've been studying the piston in the cylinder, have we not? In the study of internal combustion engines, because it's what's happening. You have that piston moving back and forth, sliding. It's reciprocating motion, a linear motion in the cylinder. When you put it with a crank with an offset, you can get rotational motion. Then that goes down the drivetrain, and away we go. Let's now talk about the four-stroke cycle. This is common in our diesel engines as well as spark ignition engines for gasoline. So what happens is you have this piston, and I have shown it in red, and it's going to move back and forth in the cylinder. So at a different time, it's moved, now it's at the top. And at a different time, it's moved to the bottom. Notice that it's connected to this rotating shaft, and this is the offset. And so when the shaft is rotated such that the pin is connected to that offset right here with this connecting rod, it's now at the top. And then after it rotates another 180 degrees, it'll be at the bottom. Then it rotates another 180 degrees, it'll be at the top. That's how you get the linear motion, the reciprocating motion in the cylinder. It's connected to the crank that way. Okay, so what happens when the piston is coming, when it's rotating, that part of the connecting rod is right there, right there, right there. It's moving this way. It's rotating, right, in the clockwise direction. It's coming down. It's coming down. And just from mechanics or kinematics, when it gets to this point and then it transitions, now the piston's going to be moving up in the cylinder. So right when it comes all the way down, and it's aligned perfectly as shown, straight down, the piston's changing directions. It's going from downward to upward. And it's at the bottom, so we call this bottom dead center. Bottom dead center. It actually comes to rest. And then back up again it goes. How about over here? This is called top dead center. Then we're back to bottom dead center. Then we're back to top dead center. Then we're back to bottom dead center. And so what we're going to do is we're going to look at these strokes. This is a stroke. That's one stroke. This is a second stroke. This is a third stroke. And this is a fourth stroke in a four-stroke cycle. Meaning this ending state is the same as the beginning state. And you're ready to do it again. You're ready to go again. So what are the four strokes? You could do a couple different ways. But let's just start how I've shown it. Let's just start right here. And I'm going to think about this as a fresh air-fuel mixture. It's a fresh air-fuel mixture. And notice that volume, that the fresh air-fuel mixture is its largest volume. And as it undergoes this stroke, what happens to that fresh air-fuel mixture? There's no valve letting anything in or out. It's trapped. So it becomes compressed. Yeah. So if you wanted, you're the first one to observe this, you would give that stroke a name. You would think, well, what's happening during that stroke? I'm taking a large volume and smashing it to a small volume. I'm compressing the gas in there, so they call it the compression stroke. Compression stroke. All right, now that you have it up here, what's going to happen is the spark is going to make that air-fuel mixture combust. Okay, so think about spark ignition. We can talk diesels next time. This is just Otto cycle spark ignition. And then you become very high temperature, very high pressure. And it's not all just at top dead center. It takes a while for the combustion to take place. So it's actually the spark kicks off a little before it gets to top dead center. Maybe a few degrees, maybe 10 degrees of the crank, 20 degrees of the crank. Or if you're really going fast, it'll be 30, 35 degrees. And probably some people here can tell me what is the typical, at idle for their engine, they have a timing light. Maybe you've done that in the garage. Sat there, okay, I've got to disconnect this and that so that it's not going to be advanced. It's just going to be a natural advance. Maybe it's 10 degrees at 750 RPM. So you set it. You set the timing. You used to have to move the distributor. Anybody? One person. Two. Okay, you're showing your age. Or you're showing the age of the vehicles you worked on. But anyway, the timing light, some people are like, what's that? No, we still have them. And anyway, so think, but for here, that change going from the air-fuel mixture to combustion products is pretty fast. And we now have something that's very high temperature, very high pressure. And when it goes down, it's going to be pushing and expanding, forcing that piston down. This is the only stroke you get power out of the cycle. Okay, so they call it the power stroke. And it's just like that boundary expansion work that you've calculated again and again. That's it. The integral P dV, yeah, that's it. That'll give you the boundary work to push down the face of that piston. Then you're at the bottom dead center again. Here, you don't have fresh air fuel anymore. You have combustion products. So you'd like to sort of get them out of the way. So what happens is when it gets to bottom dead center, a valve opens. And the way that these valves are, I almost need to see one, but they're like poppet valves basically, and they push on part of it, and when they push it in, the stem goes in and it opens up a big cavity behind it. And so the gases can rush around on the back side of it and go out like that. So they open it at bottom dead center. They leave it open during the next stroke as the piston moves back to top dead center. And as it's going to top dead center, guess what's it's pushing out that valve that's open? The exhaust products. So guess what stroke they call that? The exhaust stroke. Yeah, that's the exhaust stroke. Then they have to close the exhaust valve. So the exhaust valve, here is your exhaust. It opens, it stays open, then the exhaust closes. They have to open another valve, maybe we show it right here, at top dead center. That's our intake valve. And they leave that valve open during this other stroke, this last stroke, where the piston's going from top dead back down to bottom dead. As it's going down, it's drawing in a fresh air fuel charge. So that stroke, they call it the intake stroke. So somebody could have said, why didn't you start with the intake stroke? Okay, fine. We'll talk intake, compression, power, exhaust. It's a cycle. It just continuously repeats, right? How many people ever got on the highway and they look, they have a tachometer, their engine's running at 2,000 RPM. You know how many times that cycle is being repeated? That's a very, very, very fast operation, going again and again and again, okay? We should make that calculation, but not right now, okay? But so here I just started with the compression stroke, and then the power, then the exhaust, then the intake. Okay. Okay. We'd like to plot this on a pressure volume diagram. Here is an abbreviated version. It's top dead center, down the bottom dead center. What's happening right here? Oh, it looks like I started with the intake stroke, didn't I? That's fine. And then we go to the compression stroke, then the power stroke, and then the exhaust stroke. And notice I put, okay, the intake valve is opens and closes during the intake stroke. And the exhaust valve opens and closes during the exhaust stroke. All right. So we have to, I'm trying to draw this for a real operating engine. Then we'll introduce the Otto cycle approximation. First of all, put in right here 1 atm. Why? That's the air pressure outside your engine. The air pressure in this room or wherever the engine's operating. And what happens during that intake stroke, think about it, we're going to plot the pressure of the gases in the cylinder. That's the gas, in this cylinder right here. That's the pressure. And it has to be lower than atmospheric pressure. Otherwise, you're not going to ingest any air-fuel mixture. It has to actually draw it across your air filter, through the tubes and ducting of your intake manifold. Maybe you have a throttle body or carburetor, has to draw it through there, but they're pretty well gone now. And most of you run with your foot fully on the gas pedal, so it's wide open throttle, so there's no restriction in the butterfly, right? But if you're idling, there's going to be a restriction in other places in your intake. And so it's in a vacuum. So as you're going from a top dead center, which is a small volume, to the bottom dead center, which then has the largest volume for that gas, it's going to be drawing it in under atmospheric pressure in a state of vacuum. And actually, how's your power brakes works, right? Don't they run off the vacuum? A lot of the mechanical dampers moving for your air control, like I want the air to blow out at my feet, or I want the air to blow out on my window or windshield, front windshield, or I want the air. They used to all be vacuum operated. I don't know now. I haven't been under a dash in a long time. But they would have vacuum used for a lot of things inside your car. Anything else that I'm forgetting? Power, the booster on your brake is vacuum. Timing advance on older ones, right? That would be a vacuum on your distributor, timing advance. I'm trying to think. Anyway, so it is under a state of vacuum, right? And if you have a vacuum leak, anybody had a vacuum leak on the intake manifold maybe? The gasket? Yeah, had to replace a few of them. Well, how do you normally check for a vacuum leak? You take a little spray can of flammable fluid and you spray it where you think there's a leak. And if you spray it along that crevice and the RPM of the engine goes, zooms up, right? You just discovered where your vacuum leak is, because as you sprayed it, it got sucked in at that point. It's not supposed to be able to be sucked in along a leaky gasket. Or if you spray it and nothing changes on the RPM of your engine, then you know. What do you spray in there? Like a starter fluid? Yeah, starter fluid. It's actually an excellent way to diagnose problems. Okay, so let's press forward now. We're understanding it's under state of intake. Then it gets up here at the bottom dead center. It's going to stop. The pressure is probably going to come up. And as it starts to compress and go to the compression stroke, the pressure is going to go up, 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 right? And then it's going to be near the top dead center. Maybe the spark kicks it right here. It starts the combustion near a few degrees before top dead center. And then it's going to be rapid rise in pressure. And maybe the combustion ends, but now you're beginning what stroke? Yeah, so this was our intake stroke. This is our compression stroke. This is our power stroke. High pressure, pushing down that face of that piston. You're getting work out of the cycle. And right about here, another valve opens. Exhaust. Whatever. Exhaust valve opens right there. This pressure right there, when the exhaust valve opens, when you have your foot fully on the throttle, when you're doing a wide open. I know if you're idling, it's not going to have such a high boost like that. It won't be as separated between here and here. This is a visual image of the work you get out. So the way I'm sketching it, the pressure during the power stroke is a lot higher. Okay. Anyway, this pressure at the end of the power stroke is still significantly above atmospheric pressure. And as that exhaust valve cracks open, we now know why we have mufflers. Yeah, because if you don't have a muffler and you're doing this, going, down the street, heavy, foot fully on the throttle, right? You're just wide out, ripping down the street. People a mile away can hear you. Yeah, because there's a big pop and there's a quick blowdown of exhaust gases, but there's still quite a few exhaust gases in there. And then you go through the last stroke. What is that stroke? Exhaust stroke. And now notice the exhaust stroke is a little above atmospheric pressure because you've got to push it past that exhaust valve, out through the exhaust manifold. Oh, you got a catalytic converter, got to push it through the catalytic converter, got to push it through the muffler, through the little tailpipe section, and finally dump it to atmospheric pressure. So there you go. So that's the PV diagram of a 4-stroke internal combustion engine. Here I'm showing with the spark ignition. All right. And a very rapid combustion. Maybe the combustion's pretty well done. I know it takes more than that to be finished, but diesel fuel is a little different. We'll do that later, talk about it later. All right. We've talked about displacement volume. We've even sketched this pressure volume diagram or specific volume diagram going from the top dead center and bottom dead center. And what exactly is this displacement volume? Somebody says, oh, my engine is a 2.2 liter. Oh, no, my engine's a 5 liter. No, I have a 350 cubic inch. Oh, I have a 1.8 liter engine. So what exactly is our displacement volume? Yeah, that's all it is. So basically, you have a volume at bottom dead center, and you have a volume at top dead center, and the volume that's displaced is not that hard, is the volume, the largest volume when it's at bottom dead center, minus the volume at top dead center. Make sense? So if you have a, I don't know, let's say I have a 2.2 liter engine, but it's 4-cylinder, well, they're reporting 2.2 liter for the whole engine. So if I wanted what's my displacement volume for 1 cylinder, not too hard, take the 2.2 and divide by 4. That would give me my displacement in liter for 1 cylinder, my displacement volume. Okay, another piece of information that we need to know is, let me do this one. What is the compression ratio? And I'm going to move back to this slide because I invested and put some notation on this slide. So what is my compression ratio? R is my compression ratio. Now somebody else volunteered to help me with the displacement volume, but I had some help up here in the front. So who was the one that wanted to help me with the displacement volume, but I didn't call on him? I'll now call on you for the compression ratio. Who is going to volunteer to help me with the compression ratio? I thought I saw a hand over here. What is the definition of my compression ratio? Remember I said it was about 9.5 for my engine? Probably 5, 6, 7 people. Oh, I have a 10. Oh, mine is 10.5 for my engine that I run with. And somebody said, hey, I souped mine up and I have an 11. Okay. What do you have?
The volume of the top divided by the volume of 1.
Okay. Let me do this. I'm going to put out 4 choices, and I'm going to pause. I'm going to walk around, and we'll see what you say. So we can talk about the pressure when it's at bottom dead center, and we can talk about the pressure when it's at top dead center. And we can also talk about the volume at top dead and the volume at bottom dead. So here are, I'm going to make some more room here. Here are some 4 choices. The compression ratio R. Is it equal to either the pressure at bottom dead center divided by the pressure at top dead center, or the pressure at top dead center divided by the pressure at bottom dead center, or the volume at bottom dead center divided by the volume at top dead center, or the volume at top dead center divided by the volume at bottom dead center. If I was using clickers, I'd say push your button, give me your choice, A, B, C, or D. But I'm not using clickers, so I just get to walk around and observe.
My compression ratio.
So most of you have it. It is a volume ratio. And so it's the volume, the large volume. Remember the compression ratio, it's around 9. Well, it's not 0.9, it's like 9. It's larger than 1. So we start with the larger volume. That's at the bottom dead center, isn't it? And then we divide by the smaller volume. That's the volume at top dead center. So C is the right answer. Thank you. Sometimes people will confuse it with pressure ratio. And guess what? You're just a little ahead of the other students in the class. If you thought it was B, bottom dead. Oh, a lot of people were picking B. Well, when we get to the Brayton cycle and you have a gas compressor, you're going to talk about the pressure ratio across the gas compressor. Very confusing. Sorry, that's just sometimes the way it is. But inside an internal combustion engine, it's a volume ratio. And that's what they call the compression ratio. Let's save some potential confusion for later. All right, air standard analysis. Well, this is too complicated of a system, so what we have to do is we have to have some assumptions so we can make it solvable. We want to make it a simpler system to analyze. So we're going to focus our study on a fixed amount of air that's trapped in the piston cylinder. Forget the intake, forget the exhaust. This one little chunk of air is just going to be squeezed and heated and expanded and cooled and squeezed and heated and expanded and cooled. Got it? That's just going to go in a cycle. It's always going to be air. It's never going to be combustion products. Hey, that's a pretty bad assumption. It's close enough, and we're going to make some useful observations using the air standard analysis. It's always behaves as an ideal gas. That's good, and that's a good assumption. It's PV is equal to RT is always true. Any state in the cycle, any place in the cycle, as well as U is a function of temperature only and enthalpy is a function of temperature only. Those are the three things that you should remember when somebody says employ the ideal gas model. It's not just PV is equal to RT. That's true. That's 1/3 of the story. The other 2/3 are internal energy is only a function of temperature when it's an ideal gas, and the enthalpy is only a function of temperature for an ideal gas. Combustion process is replaced by a heat transfer. Things got hot during the combustion process. Why don't we just forget about the combustion? It's too complex and just make a heat transfer to make them get hot. And it's going to come from some external source, and it's going to be isolated at top dead center for the Otto cycle for sure. No intake or exhaust processes. The exhaust and intake are replaced by heat transfer to an external source at bottom dead center. And all processes are frictionless, internally reversible. Sigma during the process is equal to 0. Isn't our symbol for sigma, the entropy generation, isn't that 0 for internally reversible? Yeah. All right. So why do we do this? So we can do some calculations. If you see the additional word cold in front of air standard analysis, it's everything to do with the air standard with the additional piece of information that you're going to assume constant specific heats evaluated at some ambient temperature. I know 25C is not exactly the same as 300 Kelvin, but either it'll be like this or like that. Typically, I run with 300 Kelvin. Although a lot of places, it's at 25C. Great, fine. There's not much difference, right? Okay. So you can really make some simple calculations with that assumption of being cold, having a constant specific heat. You ready to press on? So now we're going to study this Otto cycle. The Otto cycle has 4 processes from state 1, 2, 3, 4. Here are the processes. Adiabatic compression followed by constant volume heat addition, heat transfer addition, adiabatic expansion, and constant volume heat rejection. Okay, quick question. For all of these processes, for our ideal Otto cycle, doing an air standard analysis of Otto cycle, are all those processes reversible? Yeah, that was part of the assumption. So sigma is equal to 0 for each of these. So when I write the second law for the first process, I know I probably stole, ability for you to really learn by remembering and writing the second law for a process. But this is a pretty good representation of the second law. The entropy changes because of heat transfer into the cycle, or into the substance during the process, and you could write it as the integral of 1 over TB del Q. That's true. But I just said, okay, think about TB being constant, so it's just Q over TB. And then if there's any entropy generation, that could cause the entropy to go up. So sigma 1 to 2. Okay, for the process 1 to 2, it's adiabatic compression. Can you make any observations about any of these three terms, either term, I'll call it A, B, or C? Who would like to participate? Which one is 0? C. So both of them. So if somebody said, look at adiabatic, I know what that means. That means Q is 0. Hence that term I said B is 0. Okay, somebody else said it's reversible. There's no entropy generation, sigma 0. What do you conclude about the process 1 to 2? Constant S. Oh, there's a fancy word for that. Is that adiabatic, isochoric, isenthalpic, isentropic, isobaric, whatever? Isentropic. Yeah, it's isentropic. S is equal to a constant. If you take a look at the second process, constant volume heat addition, well, this is 0. This is not 0. It's actually should be now written as the integral of 1 over TB del Q, because as you're bringing in heat, the temperature of the gas is increasing. But we'll leave it like this. But guess what? Entropy goes up. S2 will be greater than S1 because of heat transfer in. True? All right. How about now for the process 3 to 4? Adiabatic expansion. So some people who have not participated, which of these terms, A, B, or C, are 0 and why? Because it's adiabatic. And a friend behind you? Then take the other one. Sigma is equal to 0 because internally reversible. Hence, this process is S equal to a constant also. It's isentropic from 3 to 4. Now, the other one here, this is 0, this is 0, this is 0. But for the process, when you go 1 to 4, is the Q positive in when you are rejecting heat? No, this is going to be negative. Hence, when you look at it, S1 minus S4 is negative or less than 0, or S1 is less than S4. Okay, just like we concluded right here that S3 is greater than S2 during that process. Entropy goes up when you add heat. Entropy goes down when you reject heat. Okay. We're also going to take a look at the first law for each of these processes. Now let's take a look. Adiabatic compression. Is this term, the first term, A, or the second term or the third term equal to 0 if I write the first law for process 1 to 2, which is adiabatic compression? B. Good. It's 0, right? Okay. How about the work? Is that 0, positive, or negative? It's being compressed. And so from the perspective of the gas that's getting compressed, it's negative. This is negative. Isn't it? And so you have a negative of a negative, which means positive. So U2 is greater than U1. Internal energy went up. Okay. Now let's go to the second, maybe jump to the third one because it's also adiabatic expansion. So let's jump to this one. This is our third process from 3 to 4. Isn't it adiabatic? Now it's expansion. So is the work 3 to 4 positive or negative? If it's positive, but you have the negative sign in front of it in the first law, so that what about the final U4 is less than U3? The internal energy goes down. It's less internal energy at the end of that process. All right. Let's take a look now at process 2 to 3, the one I skipped right here. It's a constant volume heat addition. Which term, changing U, Q, or W is 0? You're all experts. Why is the W 0? No boundary work. You can change the pressure, but if you're not changing the volume, there's no boundary work. Likewise, if you come down to state 4, when you have constant volume, heat rejection, work. So what we find is that when you look at, you have 2 of the Q's are 0, 2 of the W's are 0. And these are non-zero. Let's circle the ones that are non-zero. But that's negative. This one is going to be positive. This one is a heat rejection, so it's going to be negative. And this one we already talked about is positive. All right. Now, let me do this. Somebody says I have 4 equations. Yep, you sure do. Can I take and add all 4 of those equations? Sure. And so if I add all 4 of them, let me say I just add them all 4, what happens to the left-hand side? These 2 terms are going to cancel because U2 minus U2, U3 minus U3, U4 minus U4, and U1 minus U1, 0. If you add all 4 of those equations. And if you add all 4 of this other side on the Q's, you're going to get the sum of all the Q's, and you'll also get minus the sum of all the W's. This sum of all the Q's is called Q net. What do you mean Q net? That's the net heat transferred into the working fluid over the whole cycle. And then this is W net. W net. What does that mean? That's the net work out for the cycle. We know that sometimes it's positive, sometimes it's negative, but when you add them together, you should get a net positive work out. So another way of rewriting this equation is Q net is equal to W net. True? Have you remember that from before? Yeah. Conservation of energy. Now that we have a good idea of all of our processes and which terms are 0 and what's greater than the other, let's put it on property diagrams. We could have maybe put it on property diagrams first, but let's now put it on property diagrams. So adiabatic compression. Should I start with a small volume or a large volume if I'm going to go and compress it? Large volume. So let's start at large volume, low pressure. That would be state 1 right there. All right? If I compress it, we just talked about it being isentropic compression of an ideal gas. Is the pressure going to stay the same? The pressure going to go down? The pressure going to go up? It's going to go up. It's going to go up. And so here we go to state 2. And hey, I learned about this compression ratio. Is that the volume 1 divided by volume 2? See, this is state 2. This is state 1. Is that the compression ratio? Somebody says, oh, I think he's working in lowercase v. Okay, the specific volume at state 1 divided by the specific volume at state 2. I can handle that, right? Yeah, that's exactly what the compression ratio is. Now, from 2 to 3, we have constant volume heat addition. So, constant volume, either the pressure is going to go up or the pressure is going to go down. Which one is it? It's going to go up. You're adding heat, and it goes up. And now you're at state 3. I'll put it over here. There's state 3, and it's pressure 3 right there. Okay. Then you're going to undergo from 3 to 4 expansion, and it's isotropic, and you have to stop it such you could follow with a constant volume heat rejection back down. So 4 has to stop right above 1. And there it is. There's our cycle on a PV diagram. You could add a little notation like this. What are they indicating right there with the little dash hash mark? Adiabatic, right? Yeah, there's no heat transfer, like insulated, adiabatic. And then they could also write something like this: S equal to C. You can't fool me. S is equal to S. C is equal to C, but S is not equal to C. No, entropy is constant. That's right. That's right. And then here they put a little Q in, and right here they put a little Q out. They know that, oh, from 2 to 3, that's heat addition, and from 4 to 1, that's heat rejection out of my cycle. Okay, now that we mastered the PV, let's jump over here and let's do the same for the TS. You're going to start at low temperature, T1, and low entropy, S1. You start there. Then we undergo a process 1 to 2, which is adiabatic compression, but we also said not only it's adiabatic, it's isentropic. So where is it? Straight up from state 1 to state 2. You're at a higher temperature at T2. And then you have constant volume heat addition. This is probably the hardest to sketch. On the TS diagram, it just goes up at a slope, volume equal to constant until you get up to state 3. Then isentropic expansion down to 4, and then volume equal to constant, heat rejection at 4 to 1. So you could, maybe you want to do that, you could add a little, hey, this is meaning adiabatic, this meaning the Q in, this meaning Q out. Those are additional notations to help you remember what's happening. So we have our first and second law for each process. We have our property diagrams. You ready to move on? Is it okay? Anybody still taking notes off of this? All right. Some reminders. Somebody says, I forgot, how do I calculate the change in the internal energy? Because didn't we have some delta U's here and there? Sure. Well, if you have constant specific heat, it's C sub V times the change in temperature. You recall that one? We're not going to use this one for change in enthalpy today, but when we get to the diesel cycle, we will. And it would be the change in enthalpy, if constant specific heats, is C sub P delta T. So sometimes you use C sub V, sometimes you use C sub P. C sub V for changes in internal energy, C sub P for changes in enthalpy. How about change in entropy? If it's constant specific heats, you could write at least 2. These are 2 that are in the book. Okay, if I could calculate the change in entropy if I knew the temperatures and pressure, how they changed. So if I knew P2, P1 and T2, T1, boom, I can use that to get S2 minus S1. Likewise, if I maybe knew the volumes and temperatures, I could get this. And then actually there's another equation. If you knew the pressures and the volumes, you could write it, but that's not write a third form of the same equation. These equations look familiar? Good. So somebody says, I have my ideal gas, constant specific heats, but they undergo isentropic process. So I look at my previous equation. The changes in S are equal to 0, are they not? And when you make that observation, you can now repackage this equation and that equation into one of 3 forms. Again, you have to remember the assumptions. Ideal gas, isentropic, constant specific heats. These are cut and paste out of that equation sheet that you have in front of you right there. Okay? And they're out of the textbook. So you get a relationship between how the temperature and pressures change, or temperature and volumes change, or pressure and volumes change. For the Otto cycle, these are our two favorites right now. When we go to the Brayton cycle, this will become our favorite. All right, but we're going to use all three equations at different times. But for the Otto cycle, these two on the bottom are our favorites. Why? Because we're going to be talking compression ratio, which is a ratio of volumes. Right? Yeah. All right. Also, you're reminded that you probably spent some time in table A20. If you needed to find the specific heat, C sub P, C sub V, or ratio of specific heats. I forgot. So back here, somebody says, I understand all the terms in this equation, but I sure don't remember what K is. What is K? The ratio of specific heats, is it not? It's defined as C sub P over C sub V. Right? All right. So you want to find the value of K, or you want to find the value of C sub V or C sub P for air at different temperatures, you can find it. Typically, we go to this table for 300 Kelvin. These are four values that you often pull out. You may pull them out so often you memorize them. It's not that you want to memorize anything. It's just that it becomes familiar. Oh, C sub P, 1.005. C sub V, 0.718. K, 1.4 for cold air. All right. If you wanted to do an analysis, oxygen, nitrogen, carbon monoxide, dioxide, and hydrogen, you can find them there also. Do we have time for this problem? I think we do. Oops. I was supposed to cover up the answers. That really doesn't matter. I'll uncover them right away anyway. So let's solve this problem. So we have air standard Otto cycle. You know, just in a few words, wow. It tells us a whole lot. But that's what we've been talking about, hasn't it? Yeah, this is Otto cycle, and we're doing the air standard analysis. It operates with 300 Kelvin and 95 kilopascal at the start of the compression stroke. In our minds, or maybe on our paper, we go back, we draw our PV diagram. We draw our temperature entropy diagram. We think about our processes from state 1 to 2, 1 to 2. Hey, that was like our compression. Then our heat addition to 3. Then our expansion to 4. And then heat rejection 4 back to 1. And so what information did they give me for this? This isn't T1 equal to 300 Kelvin? And isn't P1 equal to 95 kilopascal? They gave me information about the state 1. Then they say that the compression ratio is 9.5. All right, so I say the compression ratio is 9.5. Is it defined as V1 divided by V2? Or V2 over V1? I can't remember. The larger over the smaller. So it's going to be 9.5. The maximum temperature of the cycle is 1100. Maybe that's why I should have sketched that temperature entropy. You go at state 1 up to state 2. Then you go up to state 3. Then down to state 4. And then over to back to state 1. We did that previously. So think about this. Where do I find my maximum pressure? Where do I find my maximum temperature? Both maximums are at the state 3. All right, so they just told me what T3 is. T3 is 1100. Consider constant specific heats. Life is good. I'm going to use the C sub V of 0.718 kilojoule per kilogram Kelvin for air at that 300 Kelvin, as well as K is 1.4. So that comes out of the table we just looked at. Now determine, and they have a bunch of these parts, The temperature at the end of the compression stroke. So are they asking me for T1, T2, T3, T4, which one? T2, exactly. All right, so how are we going to calculate T2? Let me pause. I want to walk around. All right, so a lot of us were able to calculate 738. We got it from the equation that T1, let me write it as this. T1 over T2 is equal to V1 over V2. Hey, that's my compression ratio, isn't it? Yeah, it's my compression ratio, raised to the power K minus 1. Those, I mentioned that there's three very handy equations. These you'll use a lot. Which one did we just use? That middle one. That's exactly right. Now, this is like a very powerful equation. You have to know what you're doing and how you and when you can use it. But when you know what you're doing, you can solve problems more quickly. All right. So how do I get the peak pressure? Where's my peak pressure? I have to know it's not P2, is it? It's P3. This is a two-step process. So somebody says, you know what, I remember the third equation, it was very close. It was that P2 divided by P1 is V1 over V2 to the K. So what I can do, just like I calculated that T2 was 738 Kelvin, I can calculate that P2 is equal to 2,221, not Kelvin, kilopascal. I'm almost there, but it's a two-step process. Once I've now figured out what the pressure at 2 is, I look at the process from 2 to 3, and I now can solve for P3. So I helped you get P2, finish out the problem to get the pressure at 3. What is that peak pressure at 3? I'll get 5 correct answers, then we'll move on. So in the interest of time, I wish I could let everybody get it by themselves. But they have to make an observation. We used this equation and this equation when a property was constant during the process. The property was entropy. Is S constant from 2 to 3? No. Look on our TS diagram. S is way up. So we can't use any relationship which assumes it's isentropic. So, but other people that got the right answer, they said, I know there's a whole long list of properties. Just every now and then it's good to make that list of properties. The list of properties typically is pressure, temperature, volume, internal energy, enthalpy, entropy, and flow exergy, but I ran out of room. So you say, what's constant during the process from 2 to 3? Is pressure constant? No. Temperature constant? No. Bingo. Somebody observed the specific volume is constant. And then you remember this equation, PV is equal to RT. Is that true at the beginning of the process, at state 2? Yes. Is it true at the end of the process, state 3? Yes. It's true at any point during the process as well as any point in the whole cycle. It's true always, any point in the whole cycle. So what you do is you say that PV divided by T is equal to R, or that it's PV over T where you put state 2, 2, 2, 3, 3, 3, and then you say, well, V2 and V3 are the same. Bingo. So there's my relationship that P3 is equal to P2 times the ratio of T2 over T1, T3 over T2. Got it, finally. The two people that had it correct, is that what you used? Is that what you used? Yeah. So it's basically ideal gas, constant volume process. Right. So this turns out to be about 3,310 kilopascal. How about the, I needed to get rid of that. What about the heat addition for the cycle? Well, where is heat coming into the cycle? It's only coming in the process 2 to 3. So what is Q 2 to 3? U 3 minus U2. Hey, we're using constant specific heat. C sub V times 3T times minus T2, yes. 0.718, we looked that up, kilojoules per kilogram Kelvin, times the temperature 3. T3 is 1100 Kelvin, minus T2, which is 738 Kelvin. The kelvins cancel, and we're left with the final answer of about 260 kilojoules per kilogram. That's how much heat is into the working fluid in the process 2 to 3. What is the net work? How do we calculate that? There's two ways to calculate work net. You can calculate it by calculating the work 1 to 2, adding the work 2 to 3. Not 2 to 3, 3 to 4. True? Or you could also say work net is equal to Q net, and Q net's Q 2 to 3 in plus a negative or a Q 4 to 1. And so both of these work. Since we already calculated this, let's just go calculate Q 4 to 1, and then we'll add it. This is going to be negative because it's an out. This we already calculated as positive, and hence you calculate that it's around 154. How did I get that? By calculating Q's? Yeah, because Q net is equal to work net. True? And the last, because we're running out of time, what is the thermal efficiency of the cycle? Let me erase this and say that the thermal efficiency of the cycle is, I did get net work out, W net, and I had some heat supplied. And the heat supplied was my Q 2 to 3. You know what? It's the answer from the previous part, 154.2 kilojoules per kilogram. That's the answer to part D, divided by, I'm sorry, yeah, that is true, divided by the answer for part C, 259.7. Hence, the thermal efficiency comes in at a whopping unreasonably high, but hey, that's what our theory predicts, 59.4. Okay? Well, with that, I thank you for your attention. We'll continue there next time.